It is my great pleasure to invite to present Luis Lam, who will be giving a talk entitled Learning and Reasoning in Neurosymbolic AI. Luis Lam is a professor of computer science and AI at the Federal University of Rio Grande do Sul in Brazil. He holds a PhD from Imperial College London and is currently at the MIT Sloan Fellows MBA program, class of 2023. Lam has been an AI innovation and technology researcher for over 20 years. He has been a pioneer of neurosymbolic AI research, having co-authored a seminal book in the field and spoken widely about the perspectives of AI and innovation in academia, industry, and government. Lam was Vice President for Research at UFRGS University, Dean and Vice Dean of the Institute of Informatics. Lam has co-led the Alliance for Innovation between the state capital's three largest universities, UFRGS, PUCRS, and Unicinos, in the 1.5 million Porto Alegre city, and managed a successful strategy for innovation ecosystem implementation in the state's capital. He was then invited to create a new State Department for Innovation, Science, and Technology. As State Secretary, he led a large-scale innovation, science, and technology strategy in the 11.5 million people state of Rio Grande do Sul for the period 2019-2022. The policy supported and funded regional innovation ecosystem projects across the city of the state territory. As a result, the state was ranked first in innovation by an independent study by the Center for Public Leadership this year. Luis, thank you very much for accepting our invitation. I give the floor to you.
Thank you, Gerardo. Thank you, everyone. It's a huge pleasure to be together with you. I'm going to share the content now. Okay. Okay. I hope you can all see. Okay.
Yes, perfectly. Thank you.
Fantastic. Thank you so much. It's a great pleasure to be here, or actually to be online, but I wish I was there in Buenos Aires. So yes, we are going to speak about learning and reasoning in neurosymbolic AI, and this field has been active for quite some time. We had, let's say, a small number of people connected to the field and interested in the field, but over the last year, some companies have shown interest, and some people also realized that in addition to deep learning, in addition to the power of gathering, the power of dealing, managing data, in AI and in computer science in general, the problem of reasoning upon data in building machines that could actually represent in a better way the way we process knowledge, we represent knowledge, and we draw inferences from knowledge was also an important problem. So I'm saying that what we need is a better integration between schools of thought. Some schools think that, okay, machine learning is a wonderful tool for several tasks, but of course you have to be aware that there are other tools, other techniques and methodologies in reasoning, knowledge representation, in inference, in logics, and in techniques associated to knowledge representation in a way that we can better draw inferences from data. So this is the key issue that we try and work in this school of thought. And I just paid homage to some of the very famous painters in the Vatican, which is the School of Athens, because we are living through an era where knowledge and reasoning and, of course, the intellectual activity is becoming more and more important in the economics. So just a bit of the summary of our talk. We are going to talk a little bit about the different schools of AI, mainly symbolism and connectionism. And we try to show that it's possible to integrate learning and reasoning given certain conditions. And this is done via a methodology called Neurosymbolic AI. As I mentioned, has been active for some decades. And I also draw some parallels and I bring some work that points out what's the difference, not only between those three schools, but also in terms of what kind of future research and future avenues that we can pursue in this field. So I would like to, of course, to thank a lot of many collaborators over the years, and much of this work is inspired in a paper that I wrote with Arthur Garcés from City University in London in the end of 2020, and we've been updating this paper from time to time. So Recently, actually, in October, there was an issue of communications of the ACM. There was a report written by Don Morrow on what's actually going on in AI. So for those interested in neurosymbolic AI, how the combination of neural networks and symbolic representations can make AI systems more transparent, more reliable, more explainable, and in a way that we develop systems that are, in the end of the day, more robust. So there is this article that's also a very easy read, a nice introduction to the field, and it points out also some directions that are going on at the moment. There is also other interesting connections with other fields of AI and of knowledge representation, and also of science in general. For instance, Pierre Levy is developing a language to represent knowledge, and he pointed out that perhaps the best way to the question that we're trying to answer here is that from the very early age in AI, what we wanted to do was to represent and to analyze the question if machines, in the end of the day, can think or not. So the big question in AI has always been if machines can or cannot think. Even Turing, from one of his first papers, he posed this question: can we answer if machines can or cannot think? And when you think in terms of reasoning, in terms of learning, they are the two most outstanding cognitive abilities. So machine learning and knowledge representation and reasoning have been two schools of thought in AI. And the power of neurosymbolic AI is exactly what we are trying to build here. Can we harness the power of logic and learning so that they can build more robust AI systems? So in the very early history of, let's say, computer science, already we had people like John von Neumann that realized that there was a connection between artificial neural networks and logical reasoning. And von Neumann even defended the point that perhaps the best logic to represent reasoning in artificial neural networks was intuitionistic logics, because in intuitionistic logics, you can associate the difference that there is between, let's say, ordinary logic, that's classical logic, and the logic of constructive procedures, the logic of proofs in computer science, the logic of algorithms, where you have a better relation with the constructive processes that are represented via intuitionistic logics. So the relation between logic and neural networks was perceived very early in computer science, but for some reason, this particular difference, this particular observation was not pursued in terms of research. Okay, so also another interesting observation that we can do from very early on in computer science, that Stephen Kleene, one of the foremost computer science theorists, he created regular expressions to express or to represent McCulloch and Pete's artificial neural networks. And already in the 40s, early 50s, people realized, of course, that we could try and represent the processes that go on in the human brain. Of course, the abstractions that were created by McCulloch and Pete's, they were not perfect representations of how biological neurons work, but they were one of the first efforts towards building richer representations of the process that we have in our brains, the process that we have in cognition. And we've gone now for a jump into the early 2000s. It was not very common already in the early 2000s to see any connections between reasoning and learning and artificial neural networks. Even if you analyze the top AI conferences and even the top machine learning conferences at the time, deep learning was not very popular, or artificial neural networks were a bit down. But by the mid-2000s, Jeff Hinton started to show some very interesting results, some very powerful results about the power and the computational capabilities of deep belief net. We started to witness many extraordinary developments in AI research, and then it was followed up by technological applications in several businesses and several companies. And more recently now, since 2019, I would say, 2019, 2020, people noticed that, okay, we have some very wonderful applications of machine learning into several domains, in pattern recognition, image understanding. But in terms of reasoning, what can we do with deep learning in terms of processing logical inferences? And can we combine the neural networks, or use neural networks to represent not only some specific target applications in image recognition, in language, in question answering, can we actually do something related, for instance, to natural language processing that has a much more, let's say, intricate semantics, and where the applications have to be way more explainable and way more secure and interpretable. So that was the big question that brought together, researchers that realized that, okay, machine learning, deep learning is a powerful tool, but how can we move AI forward in the way that we have better applications that, for instance, represent common sense knowledge, common sense reasoning, and argumentation. So this was the debate in the early 2020s. Over the last 2-3 years, people started to talk about, okay, is it possible to have a better semantics? Is it possible actually to assign semantics to some of these wonderful tools that people are using in deep learning? And so this debate started. We had several meetings, several public debates on how to better integrate those two schools. So this is the story of how the field became a little bit more popular over the last days. Another important talk was given by Henry Kotz. When Henry Kotz got an award for from AAAI, he gave a talk about the third AI summer. That was the title of this talk, and he presented a taxonomy of neurosymbolic AI systems, framing that many applications in artificial intelligence could be seen in a way that we are actually dealing with systems that combine symbols and the learning capabilities of deep neural networks. Also in the first Great AI debate, Gary Marcus put forward the case that over the last decades, many people, including himself and including, for instance, Daniel Kahneman, they realized that, of course, there are different ways of presenting reasoning and learning. In cognitive science, this has been an active field of research. And in his book, The Algebraic Mind, he put forward the case for hybrid systems in artificial intelligence. Also, when we see these days some of the main media reports about technology, we notice that some companies, including IBM, including Microsoft, are paying more attention to these applications, because when there is a lot of pressure from people, from customers, from people who buy technology and use technology, there is a pressure. For instance, if you want to use AI in the medical domain or in AI in safety critical systems, we need better applications. We cannot offer black boxes to people. And this is one of the motivations for companies and from big tech companies to use and to investigate what's the power of neurosymbolic AI, why people in research combine the neuro and the symbolic approaches. And in terms of the motivation, Daniel Kahneman, who wrote Thinking Fast and Slow. Daniel Kahneman is the Nobel Prize in economics. Of course, he has a long history in cognitive psychology. And Daniel Kahneman has defended this approach where system one, that represents our intuitive, our fast parallel system, is more connected, let's say, to deep learning, because it is more a reactive system to situations that we see on a daily basis. Whereas system two is a more reflexive systems, where people perform symbol manipulation, where people have a more elaborate forms of reasoning. And in system two, we are reflecting upon certain situations that we have not seen before. And this requires deeper reasoning, deeper reflection, and this is connected in a way to the way that people reason about complex situations. And Daniel Kahneman also put forward that as far as he's concerned, system one certainly knows some language, and in his opinion, to manipulate language and to manipulate the way that we express ourselves in terms of conversation, in terms of reasoning and interacting in systems that are composed, let's say in AI, as we say, by multiple agents, we have to manipulate systems to have a better representation of the situations or the complexity of distributed systems or systems that require interaction between many agents. And so this is the distinction that there is. In AI, we have the distinction between what was called as the symbolic school and the neuro or the connectionist schools. Some of the first pioneers of AI, like Alan New and Herbert Simon, they developed, of course, many relevant applications in AI. The first symbolic systems, the first system that were aimed at playing chess, the first system that that were trying to make some proofs, mathematical proofs. And later on, the developments of learning were not only concentrated on machine learning in the neural network school. We have researchers like Les Valiant and Judy Pearl who presented other approaches. Valiant is known for the theory of machine learning. One of the first computational learning theory developments in terms of pack learning was proposed by Les Valiant. And of course, we have this school of thought in terms of representation of causes and consequences that is put forward by Jude Pearl, and he brought the knowledge from probabilistics and probabilistic reasoning, in particular Bayesian reasoning, to AI. So the thing here is that we have this separation between the two schools. The school that believes that, okay, neural networks is the best way to move forward. It's a powerful tool that can represent learning or machine learning and learning processes in the most efficient way. And our practices in terms of technological development show that this is the way forward. Whereas we have the symbolic school showing, well, hold on for a moment, we also need a safe way to represent the logical reasoning that we have, for instance, in mathematics, or the logical reasoning that logicians have been studying for thousands of years, and this is the proper way to represent reasoning. And so the debate moves forward and backwards along those, let's say, those two big schools of artificial intelligence. And in neurosymbolic AI, what we try to do is to find a midway, to find, let's say, a way of combine these two schools. And in neurosymbolic AI, what we do is we learn from the experience, okay, from the data we gather from the environment. We can imagine, for instance, a robot that is equipped with sensors and gather visual information from the environment. And we combine this with the ability to reason about what was learned. We can think in terms of, okay, educating a child. This is my daughter when she was quite young. She realized that she could apply the same procedure that we applied, let's say, in brushing her teeth. She realized that that was possible to learn, let's say, from the environment and apply the same procedure over her toy, right? So the motivation here is to learn from changes in the environment. The environment is, of course, very dynamic. And when you are learning from the environment, you have to think not only in terms of classical reasoning. In terms of classical reasoning, you have some simple propositions that you can represent in the proper way at the right level of abstraction. But when you think in terms of moving around an environment, you have to reason about different dimensions, for instance, space, for instance, time, for instance, uncertainty. The environment can be probabilistic. When you are crossing a street in a large town, you have to pay attention to several actors moving around. You have to pay attention to cars, and you are dealing with probabilities. When you want to cross the street, you make some mental calculations. Well, okay, what's the likelihood that I'm going to cross the street and I will have not a problem with a car that's coming about? Okay, so this is the complexity that we have to deal in artificial intelligence. We have way too many dimensions to use only one single technique that fits it all. So in the end of the day, we're trying to integrate reasoning that we associate with computation in computer science and learning. So we are combining the logical nature of reasoning and the statistical nature of learning that deals with uncertainty, that deals with a lot of data. But as we know, reasoning can be complex, reasoning can be extremely hard in computer science. And there are several approaches that deal with this problem. The approaches are motivated by several reasons. One of them is to explain. Other approaches are used to understand and to reason about open, complex environments. Other approaches try to use there's several approaches using different techniques to tackle this problem. For instance, one of the approaches is known as logical neural networks, is an approach that has been developed by the IBM research lab in the US and in other sites. They do some representation of classical reasoning and some representation of relational reasoning and predicate first order reasoning. It's a very efficient application to certain domains. Our recent approach is to understand how Boolean function learnability can be processed in deep neural networks. This approach is inspired by the theory of pack learning. We're trying to understand actually what are the limits of deep learning. This is one of the approaches that is currently under development. Another approach was put forward by a group of Italian researchers, including Marco Gori. Marco Gori is one of the pioneers of graph neural networks that are quite popular these days for a number of applications, and their motivation was actually to build networks that are explainable by construction. So given a certain way of building the deep neural networks for machine learning, given some assumptions that you take, you can, by construction, build neural networks that are explained. Other approaches combine, for instance, techniques from inductive logic programming. Inductive logic programming has been developed over the last 35 years, also to combine the power of logic programming and relational learning, relational reasoning. And some recent work combines both approaches. How can we integrate, let's say, inductive logic programming in a neurosymbolic way, where logical neural networks, that's the framework developed by IBM, can do, let's say, the reasoning procedures and the learning procedures using some representation using an inductive logic programming technique. And finally, there is an approach that was developed by a group of friends here, some Arthur Garces and Luciano Serafini, and some researchers from Sony in Japan. That's called logic tensor networks, where they use tensor capabilities of very effective learning combined with a fuzzy representation, let's say a fuzzy logic-like representation of relations into a neural setting using the typical techniques that we have in deep learning by using tensor algebra. Okay, so the motivation that we have was very clear, but the approach that we presented in our research is what we call the foundational approach, because we take logical formalization and we try to reproduce the logical steps that we do in proofs, the logical steps that we have in logical systems into an artificial neural network. The motivation here is to represent logical inference in artificial neural networks. And let's say in the late 90s, people realized that for certain kinds of artificial neural networks, for instance, if you take artificial neural networks that use semilinear activation functions, feed-forward semilinear activation functions, it's possible to show that propositional prologue programs can be computed using this kind of neural network. Okay, so since we were able to show, Arthur Garces and Gerson Javrusha was able to show in the late 90s that, okay, propositional reasoning could be represented by certain forms of neural networks. Let's try and represent richer artificial neural networks. Using richer artificial neural networks represent other forms of reasoning, say temporal reasoning, say modal logic, say probabilistic reasoning. So the question was posed, can we go beyond propositional logic in artificial neural networks? And there was a paper by John McCarthy in the late 80s who questioned some of the work that was going on in the field. And according to John McCarthy, perhaps there was a limit to artificial neural networks. They could only represent simple propositions. They could not represent relations. And since then, there has been a lot of work along other directions to show exactly that neural networks were more powerful than John McCarthy thought. And our approach to show that, sorry, I'm going to jump to the picture here. Our approach was to consider that neural networks could be seen as possible worlds. When you think in terms of modal logic, when you think in terms of possible states in computer science, when you think in terms of distributed systems, of course, when agents interact in a distributed systems, you have to be able to represent the knowledge that agents have about not only their own possible world, but the other interactions that they have with other agents in multi-agent systems. And in computer science, there was a lot of development of applying modal logics, of applying other forms of logic to certain situations in multi-agent systems, and certain test beds and certain benchmarks were produced over the years. And what we did in our approach was, okay, let's see if artificial neural networks are powerful enough to represent the logical reasoning that we have in multi-agent systems. Let's see if we can represent the way that agents interact in a limited distributed systems. And let's see if it's possible to teach agents to reason about the knowledge that they are absorbing in time, and if knowledge can evolve in time and be represented in artificial neural networks. So our inspiration was to use artificial neural networks as a representation of possible worlds, and also to represent in ensembles, in combinations of neural networks, the knowledge of particular agents. And in, let's say, by multiplying or by combining different agents and the knowledge of different agents, we could represent certain puzzles, certain problems that one confronts in distributed systems. Okay, so our inspiration was, let's analyze and let's build artificial neural networks that could represent inference, logical inference. And then we found a way of representing modal logic in artificial neural networks. And in a limited sense, in a finite universe, we were able to implement some logical inference rules that are akin to logical inference rules that one uses in modal logics, or logical inference rules that one uses in temporal logic. And in order to do so, what we had to do was to develop algorithms that would plug the logical inference rules into the artificial neural network models. And for certain different logical systems, of course, you develop different artificial neural networks. And the key here is to be able to represent the logical procedure by connecting the networks, by connecting the way that agents interact with each other using inference rules. So for each agent, we are able to train the neural networks that represent their knowledge, and we are able to train the neural networks with the logical rules that will provide, that will present the inference. In that way, what we are doing here is to train the networks to reason. So the approach is learn to reason in time, learn to reason as knowledge evolves. And the proper logic that we found that we use in our test beds were modal logic, because modal logic can represent, depending on the abstraction that we choose, you can represent time, you can represent uncertainty, you can represent the evolution of knowledge in time. That's a complex problem that remains until these days, right? So in terms of approach, you use a very simple language to represent the knowledge. We use, for instance, a kind of a Prolog extended with modal operators. That's called modal logic programming. As you know, Prolog has been extended to several operators over the years and to represent knowledge as well. And we use inductive, a form of Prolog that is able to induce rules in terms of representing modalities, in terms of representing time. And in the end of the day, what we are capable to do was show that, okay, for certain fragments of modal logics, for certain fragments of temporal logics, there are artificial neural networks that can compute the result of certain programs that are represented in these networks. And this approach is also interesting because we're capable of, okay, let's analyze if we can represent knowledge that evolves in time. For instance, in the Muddy Children puzzle, where children or agents interact with each other and exchange information, as time passes, the agents absorb more and more knowledge, and they evolve their capability of reason upon new information, with information that they're gathering from the environment. And the key idea here was, was to show that this approach was useful not only for the typical test beds that one can find in scientific papers. Let's try and apply this approach to other domains. And in software engineering, one of the tools that is very well known these days in terms of software engineering research are the tools for program verification and for model checking. And the insight here was, let's use this approach. Let's combine, let's say, a neurosymbolic module with a model checker module to learn how to evolve program specifications. And let's see if this approach can be useful in software engineering to adapt requirement specifications or to improve the specifications that we have by using a combination of machine learning and model checking. So the insight here was to use a learning module. And from the examples that we provide the model checker, from the specifications that provide the model checker, when we use the model checker, it provides counter examples, and these counter examples can be used to improve the initial specification. And by combining machine learning and model checking here, one can use the power of the model checkers actually to be an adaptive system. So the outputs that we have from the model checker are counter examples of the specification, and these counter examples can be used in the learning procedure, can be used to train the engine that we associate with a model checker. And more recently, we saw some work by David Harrell and collaborators at AAAI that show exactly an approach that was very similar to this one. They compose executable specifications with machine learning and search, and by using the counterexamples that are produced by a model checker, you get better and better models of the system that you are trying to build, the system that you are trying to represent. So we found applications as well in software engineering and in other domains. Okay, so the big aim here of this community is, of course, to understand and to appreciate the work that was done in machine learning, but also we realize that, okay, to move forward in AI, we need to have capabilities to represent inference. And inference, as I mentioned in the first half of the talk, inference can be a very complex process, and inference cannot be drawn only by using machine learning techniques, because the procedures that we use in logic, that we use in first order logic or model logic, they are highly complex. And if you take a naive approach to reason, of course, you have to confront issues of complexity and other issues related to the meta properties of logical reasoning, such as completeness, such as soundness, such as decidability, and so on. So, and in artificial intelligence, and more specifically in neurosymbolic AI, in order to confront these problems and to confront this line of research, there are many open challenges. One of the first challenges that we have in neurosymbolic AI is the proper representation of first-order logics. As you know, first-order logic is undecidable, and if you take a naive approach to represent first-order reasoning or relational reasoning, you are going to not to be able to develop sound systems, and in the end of the day, we will not be able to have explainable systems or interpretable systems, because when you are dealing with first-order logic, decidability is a key issue. So to develop a system that balances learning and reasoning is still a big challenge, it's still highly complex. The other problem that we confront in terms of reasoning and machine learning in neurosymbolic AI is how to represent common sense knowledge. Common sense representation and common sense reasoning remains a big challenge in artificial intelligence. And another associated problem that we have to confront when we deal with common sense reasoning is the combinatorial explosion of possibilities that we have when we represent common sense knowledge of agents. For instance, considering the example that I mentioned in the first half of the talk, when you are crossing a street, for instance, if you have to plan the way you cross a street for a robot, for an agent, you already have a large number of possibilities to represent from the information that we gather from the environment. And perhaps the best possible way to confront the problem of combinatorial explosion is to understand how machine learning systems deal with learning NP-complete problems. This is one of the approaches that we are investigating as well. Perhaps we can draw some inspiration and some results from the representation of these problems in computer science, where you analyze the complexity of reasoning by drawing comparisons and drawing analogies with very complex problems that we bring from the theory of NP-completeness. I'm not saying that we are going to represent common sense reasoning using the tools from NP-completeness, but what I am saying here is that common sense representation, common sense knowledge is highly complex. You have many degrees of freedom. You have many possible combinations in situations that we are trying to represent. And there is a way of dealing with combinatorial explosion that comes from the theory of NP-completeness. Perhaps there is a way of combining those two techniques. And finally, when we build AI system these days, we cannot ignore the fact that artificial intelligence is applied in every walk of life, in several application domains, in multiple application domains. And more, we will have to build systems that can combine, let's say, the abilities of artificial systems and the abilities that we as humans present. And if we can put humans in the loop in AI systems, actually, this is something that we have to confront in AI, is how to manage and how to have the best possible combination of artificial systems that deal with abilities that humans are not very good at, and to combine with our cognition, with the abilities that we have as humans to develop applications and to develop things that can improve the way that we live on the planet. In the end of the day, what we are trying to do here is to harness the power of human reasoning and computational learning to build systems that combine both abilities. In the same way that we're trying to build neurosymbolic AI systems that combine machine learning and logical reasoning, we have to be aware that in this world, in the world that we live today, more and more we have human network communication between humans, between artificial systems, and we have to build systems that can actually communicate with humans in a sound way, in a transparent way, in a trustful way, in an ethical way. Okay. Finally, what I mentioned here is another paper that was published in the communication of the ACM. It was a paper published this year in April 2022. And Sepp Hochreiter, who is one of the pioneers of long short-term memories, one of the predominant approaches in deep learning, he put forward the case for neurosymbolic AI. And in order to build general AI that has human-level abilities, one first has to build what he called broad AI systems. And these broad AI systems show different cognitive abilities. For instance, the ability to abstract and reason upon information. And he saw that one of the most promising approaches to build broad AI is neurosymbolic AI. What he called that neurosymbolic AI is a bilateral AI that combines methods from symbolic and subsymbolic AI. And what we mean by subsymbolic AI is exactly the neural network approach combined with the symbolic AI techniques that we have these days in machine reasoning and in computational logic. So there is another case here, another approach that perhaps we could pay attention is to use graph neural networks to represent the neurosymbolic process that we are investigating. And finally, I leave you with some recent literature. If you want to consult or read some surveys, there are several papers that have been written over the years. And sorry, the final message here is that to build systems that have common sense knowledge and common sense reasoning, one has to combine different techniques of artificial intelligence. And sometimes also people don't believe or don't agree with each other that we should investigate different techniques in AI. Some people think, okay, perhaps neural networks are good enough to do almost everything in AI. But I also remember this quote by Michael Rabin, who is a Turing Award winner. And perhaps what we are seeing at the moment is that computer science is a young science. We are still in a very embryonic stage. And some of the results that we are producing now are very important, are very interesting, but we also have to be aware that in science, sometimes we take some, sorry. There was something in my throat here. And in science, we have to be very cautious about what we state, what we say, because some developments, as happened in the history of deep learning, can pay off only at some decades later. And what Michael Rabin is saying here is that some very, very important results are happening in the front of our eyes, and we have to be aware of how science is developing. So thank you very much for your invitation. I apologize for my throat here. I'm kind of having some issues over here, but I'm very happy to be with you. Thank you so much.
Thank you. Thank you so much, Luis. So we have a little bit of a lag, a few seconds of a lag with YouTube and the other platform where we are transmitting. So if there are any questions, they might come in a little bit. In the meantime, I can start with a short question, especially at the last things that you were mentioning over the recent developments.
Yes.
Do you think there's a risk of neurosymbolic AI, the term neurosymbolic AI, like losing its meaning because there are so many different ways in which you can do it? And do you see that as any kind of risk, or is it just the traditional risk that we have in science in general when things become very popular?
Yeah, first I want to apologize. At the beginning of the talk, I was a bit confused because of the the hacker.
Yes, sorry, we
Yeah,
apologize. We had
yeah,
the
yeah.
settings. We had
Okay,
the settings very weak.
So no, it's okay. So that's a very interesting question. When something becomes like a popular field of research, people try and frame, say, like everything is like these days we have everything is deep learning, everything is machine learning, everyone
big
is
data,
machine learning, and so on. But the approach that we promoted here is an approach that combines logical reasoning from principles with artificial neural networks. Okay, of course you can say, well, everything is neurosymbolic because I'm using symbols to develop the programs in computer science, or I'm using reasoning in this and other ways or in certain ways. But yeah, there is a risk that let's say that the term or the terminology will be overloaded. But what the community that works in neurosymbolic AI tries to do is to develop a principal way of combining reasoning and learning. And by principal way, we mean, well, okay, let's use techniques that have been developed in logic over many decades. Let's use techniques that have been developed, for instance, in argumentation, in temporal reasoning, to combine those techniques with machine learning systems. So yeah, there is a risk that let's say the field becomes, let's say, carried out or go into another direction. But the approach that the researchers in this field are taking at the moment is to follow a more principled approach by bringing techniques from computational logic, techniques from knowledge representation and reasoning, techniques from probabilistic AI, and so on.
Great. So we have a question from the audience. Guillermo, if you can unmute. Let's see if security allows us. Yes, there you go.
Okay. Hello, Luis.
Hello.
Long time no see. The question is, it seems that neural networks have a problem in representing and managing processes.
Yeah.
And that could be a way of combining both, using the power of knowledge representation to harness the ability to create symbols from the machine learning area. Yeah. Do you agree that that vision is somewhat correct?
I agree. I think it is correct because, let's say, neural networks became very popular over the last 12, 15 years because some people are able to produce very good data sets, labeled data sets. If you think in terms of the ImageNet data sets and other data sets that are produced later, one of the key successes of neural network was that the labeling process was wonderful, was fantastic. And of course, there were developments in artificial neural networks, in the theory of artificial neural networks, the kind of activation function that he used. Jeff Hinton had some insights on using rectified linear units and so on, the way you combine the tensorial algebra and so on. But in terms of bringing the techniques from knowledge representation and reasoning, let's say we are at early stages, but what I see here, Guillermo, is that if we find the proper way of representing data or knowledge using knowledge representation techniques, and then if we find the proper way of representing or learning the logical inference rules from computational logic, then I believe we will have some very, very interesting advances, not only in computer science, but for science in general. Consider that that system that DeepMind developed for protein prediction, right? Protein structure prediction. That can be extremely useful in medical applications, in drug development, and so on. But think that if we can develop the proper way of representing knowledge about proteins or representing the way that proteins interact with each other using, let's say, logical rules, that will be a huge advancement for medicine and for science, not only for AI.
Yeah, thank you, Luz. Thank you.
So we have a question from the YouTube audience, actually from Vanina Martinez, which is related to this. She says, is logical reasoning enough to open the black boxes from an explainability point of view? So this is a pretty tough question.
Yeah. Well, perhaps the question is suggesting and is implying that it's not enough. I think it's not enough, but it's the first step. As I said, well, the approach that we are developing here, let's train the networks to do this, to learn to reason about this particular logic, like a simple, very simple model logic for some target application. That's not a solution for everything, but I believe, Vanina, it's one of the first steps that we have to do. Of course, to explain things, it's such a, I mean, explainability is such a complex process, such a complex problem. And if you think in terms of science, causality is a huge problem as well. And we are just beginning to scratch the surface in terms of neurosymbolic AI system. We are not even close to the solutions, let's say, to the big problems that we have in AI. That's a great question. Thank you so much, Vanina.
So while we wait to see if there are any other questions, I have another one that I always, as a logical, computational logician myself, I am very often very centered on questions of dealing with some of the issues that you mentioned during the talk, which are expressivity, computational complexity. And when I see these solutions, these very successful solutions that combine both approaches, I often, my mind immediately goes to the fact that computational complexity is very, very hard. It gives you a very crisp answer to this. You cannot go beyond this unless, you know, P equals NP. So this, another open-ended question, how do you see the two maybe informing each other or helping each other find solutions that the other wouldn't with tools that they have at their availability?
Yes, that's a great question. One of the reasons why we started to investigate NP complete problems was exactly the point that you are making here, Gerardo. When you are trying to represent common sense reasoning, we have a combinatorial explosion in terms of the number of possibilities, and common sense reasoning is a very tough area, perhaps because it's highly associated with the complexities and degrees of freedom that we have when you are trying to represent the knowledge of an agent. So computational complexity is still, well, of course, it's a huge issue here to confront when you are representing knowledge. But what we try to do, and what we try to do in our approach, okay, let's take a small fragment of a logic that we know this is decidable, and this in terms of complexity, okay, it's not going to take forever for us to learn to reason about this particular logic, this particular inference role. So what we take is a very humble approach, and we try to be compositional. Okay, let's start from first principles, from a very limited universe. Let's go for soundness, not completeness, because it's impossible to go for completeness. And let's go to a limited universe where we can frame a particular problem. Let's say, let's frame the muddy children problem here. Okay, you think, wow, this is a childish thing. No. But these problems offer you so many challenges when you're trying to build a system that can solve this problem, that you understand the complexity of reasoning and the complexity of building systems that can learn to reason. And that's a hugely important problem. And the question is very well posed. So that's the approach that we suggest from experience is, okay, take a very small logic fragment and compose the logical fragments as you build the system, and you build systems that are more and more complex. That's the approach that we suggest. Yeah,
that's a great way of seeing it. I hadn't considered it's kind of like thinking of rebooting and starting again and saying, okay, we have the problems, we identified the problems, like you say, that are very challenging in a very specific way, and see if dealing with them in a different way, we can get around maybe the constraints that we maybe auto-imposed by saying, okay, let's use first order logic or this fragment.
Yeah.
And maybe in this way we can combine the strengths of both, because you know, like I was saying, computational logic is very good at finding fragments that are tractable and decidable and very good computationally. But the connectionist approach is very good at saying, okay, let's actually find a solution that will work very well, that we can parallelize and that kind of thing. So I'm very hopeful that this path will lead to some very good success stories. And like you were saying that in one of the final quotes, it's a very exciting time, I think, that we are living.
Yes. Yeah, again, I apologize for the first half. I was a bit nervous by the guy drawing, but I can give a better talk in another occasion. Okay. Yes, what Michael Rabin was saying is that computer science is a young science, and we are seeing very important results happening in the front of our eyes. But
Yes.
another thing is we have to be very cautious. 20 years ago, okay, if you went to a machine learning conference, people were saying, okay, don't use neural networks anymore. They're out of fashion, they're not good. Okay, that's 20 years ago. And what happened was, in the end of the day, everyone who was saying that neural networks didn't work, they're now, everyone is using neural networks now. So you have to always be very cautious in science. Don't say, well, logic's too complex, not going to work. Well, we don't know. We don't know.
Right. I guess fads
That's not
and
scientific,
trends.
I guess. If you're saying, no, logic's too complex, you know, it's not going to work, you're taking a scientific guess. It's not a scientific methodology to say that, okay?
Right. So fads and trends are not good counselors, I guess, to scientists. That's a very good final conclusion, final thought is to finish the talk. So we have no more questions, I think. So thank you very much again, Luis, for accepting our invitation, and sorry for the trouble that we had, but I think we were able to deal with it.
No, thank you so much. Yeah, I got a bit nervous because of that, but
yeah, it hadn't happened to me
in a better way. Okay, thank you.
Thank you very much.
Okay,
Bye-bye.
bye. Thank you.